In this video, we're going to go over the second section in our chapter, which covers all about accuracy and data in all of our measurements. So let's get started on that. So now the vocabulary for this section is, again, a short list. You just need to worry about the definitions of accuracy, precision, error, percent error, and a significant figure. As scientists, we rely on our equipment a lot to give us correct information. That's how we base all of our observations, is based on the information we get from our instruments. So we need to be able to trust it in order to make the correct predictions. Now, when that doesn't happen, we get bad information, and a lot of times bad information will lead us to the wrong conclusions. So now, when is this a big deal? Well, think about maybe a pilot. They're in charge of operating an airplane, and they have a lot of instruments to give them information about the conditions around the plane and then how the airplane is performing too. So if any of these instruments aren't working, then the pilot doesn't have the correct information, and the pilot can't operate the airplane correctly. And so that could be a very bad situation because it could eventually lead to a plane crash. So again, that's one of the instances in which we need our instruments to be reliable to give us the correct information. Another example might be pharmaceuticals and drugs, the medicines that you take. If you ever read the label of the active ingredients, you'll see that it's usually only about 30, maybe 40, 60 milligrams of an active ingredient. And we've worked in our labs a little bit with the scales, that grams aren't very much. They're not very big. And milligrams are way, way smaller than that too. So again, if we are not accurate in our measurements, especially when dealing with our drugs, we might be getting the wrong dose. And getting the wrong dose might have some very bad consequences as well. If you ever had any type of surgery or you've been put under anesthesia, those anesthetics are really, really strong, and so just the right amount will put you out and you'll have no problem with the surgery. But if you get just a little too much, then it could potentially kill you. So yeah, it's very serious dealing with those drugs, and whoever is doing that job of giving you the anesthetic, you better hope that they're right in what they're doing and that they have the correct information as to the doses that they're giving you. Now, the way that we can describe a lot of our information in our measurements is using the words accuracy and precision. And so you probably already know these two words, and they might seem very similar, but there's just a very important distinction or difference that we need to go over the way we talk about it here in science. All right, so now for the accuracy, it really just means if it's a true value or how close it can be to being correct. So it should answer the question, is this measurement correct? Is it right? Whereas precision refers to the consistency of the measurements. So consistency, I'm talking about, can it be repeated? All right, so if you look at this example with the bullseye, so if you can think of taking a measurement as hitting a bullseye, you want to hit the center of the target in order for it to be correct. So if we look at this example here on the bottom right, we see that we have a very tight cluster of points in the center of the bullseye. So in this case, we could say that our shots in this one are very accurate, right? They're all hitting the bullseye, so they have a very high accuracy. Now, because they're all so close together too, we can also say that they are very precise. They have a high precision. So if we compare this over to the left bullseye, we can see that all these points, they're all concentrated around the bullseye, more or less, right? They're all hitting the center. Some of them are a little bit outside, some of them are inside the bullseye. And so, because these are all very close to the center, they're hitting that true value, we can say that they're still very accurate. But because they're a little bit more spread out than they were in the example before, they're not as precise. If you compare that over here to the top right target, again, you can see that the points are all very close together. It's a very tight cluster again, so we can say that they are very precise. We are repeating this mark over and over again. But because it's placed away from the bullseye, we can't say that it's accurate. We would say that it's not accurate. And for this last example, you can see that we have all these points scattered all over the target, and again, just one hitting the center, but then the rest are all placed away from it. So this would be something that is not accurate. And because these points are all very far away from each other, it's also not very precise. And now we come to significant figures. So now the significant figures is how we express the accuracy and specificity of the measurements that we take. So we usually deal with numbers and the measurements we use in this significant figures. So think of this example. Say that you have a piece of gold and you want to know exactly how much it weighs so you know how much money you're going to get for it. So you have two scales that you can use. You have this regular, normal kitchen scale. You bought it at Walmart for, I don't know, $15. And then you have the scientific scale that cost over $1,000. So now these two do the same job, but one of these will be more accurate. So if you actually place your piece of gold on these two scales, you get these two measurements. On the kitchen scale, it tells you that it's 82 grams. And on the scientific scale, it tells that it is 82.00218 grams. So they're basically the same, right? It's about 82 grams, so there's not a very great difference. But because this scale was able to give you a lot more decimal points, you can say that it's a lot more accurate. So notice that 82 grams, again, it's not as specific as 82.00218. So we have a very specific measurement. And so for when you're using this for a scientific purpose or, maybe the pharmaceuticals, you want to make sure that your pharmacist is using the scale that is very specific so you can get the right dose in your medicine. Now, when we talk about the degree of accuracy of a measurement, we are using the significant figures, and we actually count out how many significant figures we have in a value. All right, so what the significant figures is these are the digits in a value or a measurement that give you all the important information. These are the numbers that you want to focus on for your measurements. And it really just comes down to comparing 0 digits versus non-zero digits. And I'll tell you more about that in the next slide, but just as a short example to get us introduced to it, let's look at these two numbers. These two numbers are very similar, 102 and 120. They're within 18 points of each other, so that could be a lot, or maybe it's not a lot, depending on the scale. But again, these are both 3-digit numbers, and we have the same numbers that go into it, 1, 0, and 2. They're just in a different order. But if we apply our rules of significant figures, we'll see that 102 has 3 significant figures, and 120 will have 2 significant figures. All right, so now where is this coming from? How can we say that 102 and 120 have these different number of significant figures if they are very similar numbers? Let's go ahead and look at those rules so we can make sense of what's going on. All right, so just for clarification here, when I'm talking about non-zero digits, I'm really talking about any number that isn't a zero. So it'll be 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are all my non-zeros. Whenever you see a 0, that's just a 0. All right, rule number 1 is that non-zero digits are always significant. So if you look at a number like 1,237, well, you see they have all these different digits. You have the 1, the 2, the 3, and the 7. These are all non-zero. So in this case, just counting out the significant figures, it would be 4 significant figures. And you can compare that to the number 1,230. Yet very similar number. We have 1, 2, and 3, but notice that we have that 0 at the end. We don't really care for that 0. It's not giving us any important information as to the value of our number. So we just call this 3 significant figures. Rule number 2 is that the zeros between non-zeros are significant. All right, so if we look at the number of 102, notice that it has 1 and 2 on either side, left and right. So these are our non-zeros. We definitely want to count those as significant. But because the 0 is placed between those two, it's being sandwiched between them, we do count it as being significant. So overall, 102 would have 3 significant figures. As opposed to 120, again, same numbers we have on here, just in a different order, but because this 0 is at the end, we don't count it as being important. So instead, we just count the 1 and the 2 as being significant, and we get 2 significant figures. Rule number 3 is that the zeros that come after a decimal point are always significant. So if you take the number 1.20, again, we compared it to the 120 example. Again, same numbers, same order, but because we have a decimal in this example, it's a little bit different. Now, because that 0 is placed after the decimal, we would count it as being significant. So we would count this as 3 significant figures. And same for 10.2. Again, this 0, there's a decimal here, and it's the 0 is sandwiched between the 1 and the decimal, or you can think of it as being sandwiched between the 1 and the 2. Either way you look at it, this would still have 3 significant figures. Rule number 4 is that the zeros at the end of a number without a decimal, these are not significant. So again, if we go back to our example of 120, again, we see that there's no decimal here, so we just focus on the 1 and the 2. The 0, no decimal, we don't care for it, so we'd count this as being 2 significant figures. But if you compare that over to 120.0, essentially the same value, just written a little bit differently. But because we have this decimal in that place, it changes things. So having this decimal in this place would still count the 0 that came before it, count that as significant, and the 0 that comes after, we also count that as significant. So 120.0 would have 4 significant figures. And finally, rule number 5, this might be the most confusing one, so make sure that you pay close attention to this one. So the zeros that come after a decimal, but they are before non-zeros, these are not counted as significant. So let's actually see what we're talking about. So if we take the number 0.0120, well, if we follow that rule number 4 before, that came before, we would have this decimal here, so we would count this 0 that came before and the 0 that comes after. But actually, because these zeros come before the non-zero digits, we ignore them altogether and we just start our focus on the 1 and the 2. So we just focus on what comes after the 1 and the 2, and overall we would just count 1, 2, and 0 at the end as being our significant figures. Again, because even though we have this decimal here in this place, we start to focus on the 1, or the first non-zero digit. All right, so let's talk about how to deal with these in calculations, because a lot of the times you'll have different measurements and some of them might not be as accurate as others. So now, when you're dealing with calculations, the results that you get cannot have more significant figures than the starting information than we started with. So we can have 2 different cases. We can deal with addition and subtraction, or we can deal with multiplication and division. So let's start looking at addition and subtraction. Let's start with an example, or start with a rule. So you want to use the least number of decimal places that you have in your measurements. So let's actually look at an example of what this is. So let's say that you have these 3 different samples of water. You know what their individual volumes are, but you want to know what the volume would be together. So we can have 1.24 milliliters for the first sample, 10.8 milliliters for the second sample, and the third is 9.755 milliliters. If you take all these numbers, you put them into your calculator, you get this result that is 21.795 milliliters. But notice that I have a mismatch in all of my decimal places. So here I have 2 decimal places, 2 and 4. In the second value, I have 1 decimal place, and in the third, I have 3 decimal places. So, which is right? How many decimal places should you use? Well, the rule tells you that you should focus on the least number of decimals. So in this case, 10.8 has the least number of decimals, so you can only answer this question to the 10th place. So again, we focus on the 10th place on this one, we get 21.7, and what you have to do is that you have to drop the 9.5, but you have to follow the normal rounding rules. If you don't know what it is, it's that you focus on the last digit you're going to have, you look over to the next number, and if it's 5 or higher, you round up. If it's less than 5, you round down. In this case, we have 9, that's more than 5, so we would round up to 21.8 milliliters would be the answer for this addition problem. All right, next, let's look at the multiplication and division example. So the rule for this one, you don't really care about how many decimals there are, but you want to focus on how many significant figures each number has. So let's look at what that means. So let's say that you have a block of styrofoam or a block of wood, and you want to know what its volume is. You can calculate it using length times width times height, and this is what you get. So 12.3 centimeters times 2.45 centimeters times 4.1 centimeters. If you take all those numbers, you put them into the calculator, you get 123.5535. And again, you see the same thing where your result has different decimal places and different significant figures than the information you put in. So you need to match it to the least number of significant figures. So if you focus on the three numbers you put in, 12.3, if you count out the significant figures, you get 3. 2.45, this will also have 3 significant figures. And then finally 4.1, this one only has 2 significant figures. So again, you want to focus on the least number, in this case 4.1. 2 significant figures is the least, so you want to match your answer to those 2 significant figures. So what you do, just focus, start on the left, and you just count 1, 2 significant figures. Focus on that, so you just round off your answer to that. So your final answer in this multiplication problem would be 120 centimeters cubed. And then make sure that you only have 2 significant figures. Remember that it's 0, there's no decimal, and it's at the end, so we don't really care for it. And finally, we get to error and percent error. So it's asking a lot out of scientists for them to be perfect all the time. It's very difficult, and you probably won't get to be perfect all the time in a science lab. But in a real world scenario, there are still many sources of error, right? So we always rely on our equipment, if it's accurate and precise. We also rely on the skills of the researcher, how good they are at using the equipment, or how good they are at running the procedures. And then there's all these sorts of random error. We could list them all day, but we'll just consider them all to be, random happenings. You can't really predict them; they just happen to you. Now, that doesn't mean that science can't be trusted, but it's okay to have these errors as long as it's within an acceptable range. You don't want to be too wrong, but you can be a little bit wrong. All right, and so to calculate what that acceptable range, it could be different every time. So we have a simple formula to calculate that acceptable range. And so it's called the percent error, where we just take the experimental value, whatever you measured, whatever result you get, you want to compare that to the accepted value if it's known. And so you just take your experimental value, you subtract the accepted value, and you divide that difference by the accepted value. Then that's going to give you a small decimal answer. You just multiply this by 100%, so you can get it in a percent form, and this gets you that percent error for whatever experiment you ran. Now, generally speaking, you want to keep your percent error to be less than 5% for it to be acceptable. All right, so here we are talking about it. We're looking at a formula. Let's actually put it to an example so it can make a little bit more sense. So again, here's that formula again, so you don't forget it. But let's say that in this experiment, you're measuring the density of a lead pipe. Now, the accepted value, the target you want to hit, that the density of lead is 11.34. But now, you run through your calculations, and your answer that you get is 10.96 grams per cubic centimeter. Your partner got something a little bit different. They got 12.13 grams per cubic centimeter. All right, so clearly neither of you hit it on the head, but what we have to see is if you are within an acceptable range. So let's go ahead and plug in your value into our density formula. Sorry, this is not the density formula, this is the percent error formula. Plug your density into the percent error formula. So here you have 10.96, this is your experimental value, and you subtract the accepted value of 11.34 grams per cubic centimeter. You divide that by that same number, 11.34 grams per cubic centimeter, and you multiply by 100 to get in a percent form. The answer they get is negative 3.351%, which means that you were 3.351% under your target. All right, well, it's not too bad, but let's see how your partner did. So if we do the same thing and we just plug in their density for the experimental value and subtract that same accepted value of lead, you run through the calculation again and you get 6.966%. So this means that your partner was almost 7% over the target that they wanted to hit. And so now remember that you want to keep your percent errors to be less than 5%. So for you, you got a good enough answer. You don't need to change anything. But Whereas your partner, almost 7%, that's outside of our acceptable range. So your partner's answer would not be accepted. All right, and that does it for this short section. In the next one, we'll be going over the scientific notation and conversions, and we'll be continuing to use all those significant figures. And I think after seeing that scientific notation section, the significant figures will make a little bit more sense.